Hello guys, my name is Carlos, I'm Portuguese, so I will beg your pardon if I make some mistake here. You can comment that. On this video I'm going to talk about mathematics and an introduction to complex numbers. Before I go further, let's start with this quadratic equation: x squared minus x plus 1 equals 0, and if we apply the quadratic formula we will reach this result here. This will lead us to x equal 1, more or less the square root of minus 3 dividing by 2. So we will have here a problem. We have here square root of a negative number, and this has no solution with the real numbers. So we can say that this equation has no real roots, or it has no solution in set R, the real numbers. So this problem nowadays appears many times in electrical engineering and other engineering subjects, physics and mathematics. And since the 16th century there were some folks trying to work around this issue. So nowadays we have the notion of the complex numbers or imaginary numbers. What does this mean? Let's see. We have now a new set, the set C of the complex numbers, and it is contained by all real numbers united by this new number here, I. This number is called an imaginary number. This number has this particular solution: e squared equal to minus 1, which means that I is equal to the square root of minus 1. Okay, so now if we try to solve our equation with complex numbers, we can see that we can transform this minus 3 with 3 times minus 1. This minus 1 is I squared, and if I put the I squared outside the square root, I will have this solution: 1 dividing by 2, more or less the square root of 3 dividing by 2i. Which means that we have now a solution, but it is a complex solution, and we have x equal to 1 dividing by 2 plus square root of 3 dividing by 2i, or x equal to 1 dividing by 2 minus square root of 3 dividing by 2i. So this is the solution of our equation, but with x belonging to the set C. X is a complex number. Now let's try to understand a little better how we can represent these complex numbers. Let's start with Cartesian coordinate system or Cartesian form. In this case we have a complex Z, and we can say that it is equal to a plus a IB, where this A, we can say that it belongs to the real part of the complex. A is a real number, and it is the real part of our complex Z, and B belongs to the imaginary part of my complex Z, A plus IB. So for instance, if we get our first solution of the equation, x equal to 1 dividing by 2 plus square root of 3 dividing by 2i, we can say that regarding this complex number, we have the real part of this complex number is equal to 1 dividing by 2, and the imaginary part is square root of 3 dividing by 2. Simple enough. Other way to represent a complex number is with the polar coordinate system or polar form. this case we have our complex number represented by a z equal to a r times cis theta. So these r here, we'll see it will be the modulus of our complex. This theta it will be an argument, and cis it means cosine I sine. We'll see this a little bit further. So let's start now to understand this r and this theta and how can we calculate them. So this r is the modulus of our complex, and it is equal to the square root of a square plus b square. This ab is the real part and the imaginary part that we used in the Cartesian form. So, and theta is the argument of our complex z, and is the arctangent of b dividing by a. Again, this a and b belong to the Cartesian coordinate system that we used before. So, to have a better understanding on complex numbers, let's introduce the complex plane or the Argand diagram. So, we can draw the Argand diagram in a Cartesian system where the horizontal axis will have the representation of the real part of a complex, and the vertical axis will have the imaginary part. So we can say that we have here our complex r equal to modulus z. It is the length of this vector here. You can see this as a vector, and the argument is this angle here between this vector and the real axis, and we have the angle theta that is the argument of our complex z. Anyway, I'd like to say that this solution here, arctangent of b dividing by a, is true on this quadrant of the complex plane, which means that it is true to any angle between 0 and p dividing by 2. So let's see now how can we convert between Cartesian and polar forms. It's not that hard. For instance, let's start again with our Argand diagram. We have here our complex represented by a vector of a length of the modulus of z and an angle theta, which is the argument of our complex z. So we can say that we have here a projection of our complex on the real axis, which is a, and in the vertical axis, in the imaginary axis, we will have this b here, the projection of the vector in the imaginary axis. If we have the values of a and b, we can calculate the modulus of our complex by using this expression here, square root of a squared plus b squared. And to calculate the angle here, the theta, we will have the arctangent of b dividing by a. On the other hand, if we have the modulus of our complex and we know also this angle here, and we want to find the values of a and b, let's remember something from trigonometrics. If we remember, in the trigonometric circle, in the horizontal axis we measure the values of the function cosine, and in the vertical axis we have the sine function. So very easy. To get the value of a, we have that it is equal to r times cosine theta, and this b here, we can get this b with r times sine theta. If we now pick up these two solutions here, so we can say that we can write the complex in the Cartesian form, having z equal to r cosine theta plus I r sine theta, where this r cosine theta is our a and r sine theta is our b. Now if we look also to the polar form, I've talked to you about this r cis theta, and we can say that this cis, it's an abbreviation of this cosine theta and I sine theta. In other engineering subjects, we can also find the polar form represented by z equal to r times e raised to I theta. This is the Napier number, and this is also representation of our complex in the polar form. Now, before I go to the next slides, let me try to introduce here something that will help us understanding a little better these equations here. So, if you look at this and try to imagine this as a right triangle, we'll have the b on this side here is the same I, so it's okay, and we can find here a right triangle. Remembering Pythagoras' theorem, we can say that the modulus of our complex number could be seen as the hypotenuse, while a and b will be the sides of our right triangle. A will be the adjacent side and b the opposite side. So, and again remembering the Pythagoras theorem, we'll have that the square of the hypotenuse will be equal a square plus b square, which means that the hypotenuse will be the square root of a square plus b square. So, if you look here, is exactly what we have to determine the modulus of our complex z. If you remember also some aspects of trigonometry, in a right triangle we have that the tangent of angle theta will be the opposite side b dividing by the adjacent side a. So we have here theta, which is the argument of our complex z, equal to the arc tangent b dividing by a. Again, recalling these definitions of the Pythagoras theorem, we'll also have that the cosine of an angle theta will be the adjacent side dividing by the hypotenuse. So we have here a equal to r times cosine theta, and if we put this r in the other side of the equation, we will have cosine theta equals to a dividing by r. So it will be the adjacent side dividing by the hypotenuse. Very simple. And also for the sine of theta, we know that it will be the opposite side dividing by the hypotenuse. So we have here p equals to r times sin theta. If we recall the Pythagoras theorem, all these expressions will be very easy to understand. Now let's see an example of a conversion from Cartesian to polar form. For instance, we can use again the first solution of our quadratic equation, x equal to 1 dividing by 2 plus the square root of 3 dividing by 2i. So if we want to convert this complex from this Cartesian form to the polar form, again we can try to use the Argand diagram to understand it better. So we have here our complex, which is defined by these 2 points here, one dividing by 2 and square root of 3 dividing by 2, the real part and the imaginary part of our complex, and we have here this vector. Using the expressions we saw before, we can say that the modulus of z is the square root of 1 dividing by 2 square plus the square root of 3 dividing by 2 square, which is equal to square root of 1 dividing by 4 plus 3 dividing by 4, which is 1. So we can say that modulus of our complex is 1. Now, to determine this angle here, the argument of our complex, we can say that the argument is the arctangent of this division here, which means that is the arctangent of square root of 3, and this is p dividing by 3. So our angle of our complex number is given by theta, the argument of our complex, and it is p dividing by 3. So we can now easily write our complex in the polar form by saying that x is equal to cis p dividing by 3, where p dividing by 3 is our argument and the modulus of our complex is 1. Now, let's see an example of a conversion from polar to Cartesian form. And let's consider our last result. Now we have this complex here in the polar form, and we want to have it converted to the Cartesian form. Again, let me remember you that this expression may also be given by this e power to I p dividing by 3. And again, let's use the Lagrange diagram to help us in these calculations. So we have here the modulus of our complex, which is 1, and its argument, which is p dividing by 3, and we want to determine our a and b. So our a, which will be 1 times cosine p dividing by 3, which is 1 dividing by 2. So we will have now the solution for our a, which is 1 dividing by 2. And b will be 1 times sine of p dividing by 3, which is the square root of 3 dividing by 2. So we have now our solution to b, which is square root of 3 dividing by 2. Extremely easy. So we can now write our complex in the Cartesian form as x equal to 1 dividing by 2 plus square root of 3 dividing by 2. Now, let's talk about some operations we can do with complex numbers, and start with addition and subtraction. To do this, we need to have our complex in the Cartesian form, or the Cartesian coordinate system. So, let's consider the following. We have a complex z1, which is equal to a1 plus ib1, and the complex z2, which is equal to a2 plus ib2. So if we want to get the result of the addition of these two complexes, we can use the following expression. z1 plus z2 is equal to the sum of both real parts, a1 plus a2, and the sum of the imaginary parts, b1 plus b2. Quite simple. And the subtraction, that one will be given by z1 minus z2 equal to the difference between the real parts, a1 minus a2, plus I, the difference of the imaginary parts, b1 minus b2. Let's take an example, and for instance we have this complex z1 which is equal to 5 plus 3i, and z2 which is equal to 4 plus 2i. So we have here the real parts 5 and 4 and the imaginary parts 3 and 2. So the addition of these two complexes will be given by z1 plus z2 equal to the sum of the real parts 5 plus 4 plus the addition of the two imaginary parts 3 plus 2. The result will be 9 plus 5i. Not that hard. The subtraction, that one will be given by z1 minus z2, which is the difference of the real parts 5 minus 4 and the difference of the imaginary parts 3 minus 2. So we will have 1 plus I. Now let's see what happens with multiplication and division on a complex number. Well, we can do these calculations using the Cartesian coordinate system, but that calculations are a little bit harder, and we talk about them on another video. Now let's focus in the easier way, which is by using the polar coordinate system. So if we have a complex z1 equal to r1 cis theta 1 and a complex c2 equal to r2 cis theta 2, let's see how can we do the multiplication and division of these two complexes. So the multiplication will be given by z1 times z2 equal to r1 times 3 which means we will have the multiplication of the modules of both complexes, and cis of theta 1 plus 2 theta 2, which means the sum of the two arguments of our complex. The division will be given by z1 dividing by c2 equal to r1 dividing by r2, which means we will divide the modules of the two complexes, and we will have cis theta 1 minus theta 2, which is the difference of the arguments of our complex numbers. Now let's take another example. Imagine that we have these two complexes here, z1 equals to 3 cis p dividing by 3 and z2 equal to 2 cis 4p dividing by 3. Let's see the results of the multiplication of these two complex numbers. We will have then z1 times z2 equal to 3 times 2, the multiplication of the modules of the two complex numbers, cis p dividing by 3 plus 4p dividing by 3, which is the sum of the two arguments. And we will have this result, 6 cis 5p dividing by 3. Regarding the division, we'll have z1 dividing by z2 equal to 3 dividing by 2, the division of the modules of the complexes, cis p dividing by 3 minus 4p dividing by 3, the difference between the arguments. And we'll have this result 3 dividing by 2 cis minus p. Now let's see another property of complex numbers. It is called complex conjugates. To understand this property, I'm going back to the Argand diagram. We have our complex number here, z equal to a plus ib, and we say that conjugate of a complex number is given by z star equal to a minus ib. This notation here, you can also have a z with a line above, but I prefer to use this notation here. And what does this mean in the Argand diagram? So we will have a kind of a mirror of our complex here, around the real axis. So we have now this new complex here, which is the conjugate of this z equal to a plus ib. Now if you can see, the model of the conjugate is equal to the model of the complex. So what is different is the angle. The arguments of the complex will take a different signal. So if we have here a theta, we will have now minus theta. So it will be easy also to determine the conjugate of the complex in the polar form. It will be z star equal to the models of the complex z cis minus theta. Simple enough. And for instance, if we pick up the solution of our quadratic equation that we saw at the start of this video, we'll see something funny here. The results are conjugates. So this is because we have in the quadratic formula more or less the square root of b squared minus 4ac, and this will give us here a sign plus and a minus, and the results are conjugate. Now regarding complex arguments, we've seen that when we have the real part and imaginary part both positive, we'll have our complex number in the first quadrant of the argument diagram, and we have our argument between 0 and p divided by 2. So the expression to determine the argument will be arctangent b dividing by a. But now what's going to happen in the other quadrants? Well, if we have our argument between p divided by 2 and p, the argument will be given by arctangent b dividing by a plus p. If we have both real and imaginary parts negative, we'll be on this situation here with our arguments between p and 3p divided by 2, and the argument will be given by arctangent b dividing by a minus p. If we have a positive real part and negative imaginary part, our argument will be between 3p divided by 2 and 2p, and the arguments will be given by arctangent b divided by a. Just like the same situation we have here when we have both imaginary and real parts positive. Now I'm going to finish with two special cases. Let's imagine that we have a complex number that the real part is 0 and the imaginary part is different from 0. So in this case we'll say that our argument will be in more or less p divided by 2. This means that our complex is somewhere in the vertical axis of the Argand diagram. So in this case we can say that our complex is a pure imaginary number. Now if we have a complex number that the real part is different from 0 and the imaginary part is 0, we can say that the argument of our complex is in 0 or more or less p, which means is over the real part axis, and in this case we have just a real number. It has no imaginary part, and so it is called a real number. You may ask also what will happen if we have both imaginary and real parts 0. Well, in that case the arctangent of 0 divided by 0 is an indetermination. We cannot determine that result, and in that case we say that the complex number is indeterminate. Thank you for watching this video. I'll be posting new videos soon. Please feel free to subscribe my channel and place your comments, and that's all folks by now, and thank you again for watching this video.